A window.
Welcome you all for this webinar.
Give me a second. I don't usually use Meet, so I'm puzzling my way out here, but I'll be with you shortly.
Yes.
All kinds of permissions I have to give.
Yeah. You please take your one time. No problem.
Okay, thanks. Oh, now I've got to quit Chrome and reopen. Good Lord. Give me a second. Sorry about this. Hello? Do you hear me all right?
Yeah, yes, sir.
Oh, good. And am I sharing the presentation or something else? You see this? You see the slide?
Slides? No, right now.
You don't see the slide?
No, sir.
Okay, hang on.
Sorry.
I'll try this again, shall I? So you don't see the slide still, huh?
No,
Not it, sir.
not yet.
Okay. I'll stop and
Came,
start again.
it immediately disappeared.
Sorry?
It came but immediately disappeared.
Really? Dear Google, give me a second. Okay, I'm going to try again.
Yes.
Is that better?
No,
No?
no in the sleep.
How strange. Stop presenting, sharing entire screen. It says I'm presenting the sharing the window.
Shall we try?
You don't have the presentation, though, is the only problem. You've only got a PDF. That's not really it. Let me try sharing the whole window and see if that works. Hang on.
Oh, it's up.
Yeah.
Oh, you got it?
Now it's
Now we
a
are able to see.
Okay, good.
Yeah.
Is it clear? You see the whole, it says seminar, marine corrosion, etc.
Yes, yes, yes.
Okay, good.
Right. Just we have some introduction. Then we will start.
Okay. Now let me do one more thing here. Is everybody on now? I mean, have we got the whole audience present?
Audience. We will keep the focus after this. He's asking the audience.
Yeah, we will focus it after this.
Okay. I'm trying to, let's see, send a reaction, turn on captions, turn off camera. Okay.
For maritime policy research study, we are happy to welcome you all for this seminar.
So,
And on behalf of, I am requesting Professor Sankaran to give the welcome address. And introduce the
Good afternoon, everyone gathered here. And first of all, it's a great honor to welcome Mr. David Phillips, Special Project Subsea Industries, Belgium, for his valuable presence to give a seminar on marine corrosion. And I welcome the dignitaries who are present online. And also I welcome VC ma'am and Pro VC sir who are the valuable, for the valuable support and presence during this seminar. And you should know the introduction of these presenters before going into the seminar. Mr. David Phillips has worked since 2010 as special projects in charge for the Hydrex Group, including Hydrex Underwater Technology and subsea industries, protection and performance, marine coatings, and underwater cleaning equipments. Mr. David Phillips' work has included extensive research and writing in the area of marine corrosion and ship hull performances. In 2014, Subsea Industries received the prestigious Sea Trade Innovation Ship Operations Award for its coating EcoShield Ultimate Protection from Cavitation and Corrosion Erosion Damage for ships' hulls, rudders, and running gear. And sir, I cordially welcome you, sir, for this seminar. Once again, thank you very much.
Thank you. Thank you very much. It's an honor to be with you. And I hope that the presentation will be of value. It's the only reason for it. And it's not any kind of theory. It's not a scientific presentation. This is based on practical experience at sea. It's based on real solutions for real problems that any student who's watching this is going to encounter down the line and is going to want to know how to handle. So that's what we're covering in this presentation. Thank you very much again for the invitation. I really appreciate it. And I hope we'll all have a good time and learn a lot.
yeah, we can start now.
Okay, here we go.
Please.
I'm going to tell you just a little bit about us so you know where this information is coming from. We're a company called Subsea Industries. We have two lines of production. One is, do you see my pointer, by the way? Does that show up? Can you see the pointer or not? Someone?
yes, sir. Point.
Yeah,
Yes, sir,
Oh,
yeah.
good. You do see it. You do see it. Okay, cool. All right. We started off making underwater cleaning equipment, which is still in use around the world, but we rapidly got into coatings. And it's from the coatings point of view that I'm going to speak to you today. The company was founded by a Belgian, Boud van Rompuy, in 1983. And he's still our CEO. He's still our founder. The hulls, the coatings began to be used commercially in 2002. Hulls that were coated with that coating at that time are still in excellent condition today with no repainting, which is part of the philosophy of our coating system. I've got to warn you all that this presentation on corrosion is coming from a specific viewpoint. I'm going to tell you that everything that I tell you is going to be accurate and truthful from my point of view, but it is a point of view. If I were working for a cathodic protection company, I would give you a different presentation. So you have to keep that in mind when I give you this information, and I will also make this presentation available to you afterwards, anybody who's attending. But that's the viewpoint. So you have to take it as part of a whole picture. I'm not going to get into other factors that are involved that other people would tell you about. I'm going to concentrate on a coding approach, and we are a disruptive company. We are not generally in line with mainstream coating manufacturers. And I'm warning you about all of that in advance so that you can take the information that I give you with that viewpoint, okay? All right, what is marine corrosion? Let's start off with the basics here. By marine, we're referring to ships, structures that operate or are situated in or near or immersed in the sea. That can include offshore platforms. It can include, oh, I don't know, quay walls if they're made of metal. It can include all kinds of things that it has to do with metal in the water, mostly.
Yes, madam.
Corrosion is the gradual breaking down or destruction of a material, especially a metal, through chemical reactions. The most common form of corrosion is rusting, which we're all very familiar with. It occurs when iron combines with oxygen and water. Corrosion comes from the Latin word corrodere, to gnaw away, from rodere, to gnaw. Interestingly enough, it's the same origin as for the word rodent. And here we see North America's largest rodent. It took her 15 minutes to get through that tree trunk. So it's an appropriate word. You can understand why it's called corrosion. They used to have a lot of trouble with rats on wooden ships, you know, in the days of sail. Today, it's a new kind of rat, and it eats away the metal. It's definitely a problem. So marine corrosion is a subject of gradual wasting away or destruction of the metal which ships, offshore assets, and other man-made objects are made of, due to the effects of the sea environment in which they operate or are placed. So that's what we're talking about today. It's not necessarily the entire subject, but that's what we're going to cover. Here are some examples for you. They're pretty horrendous. It's not always this extreme, but top left, you can see just general rust on a hull of a ship that I would be ashamed to be the captain or officers of. The third one along here is the inside of a ballast tank, and you can see that it rusts from the inside out. And in extreme cases, you may get a situation like this. I hope you never do, but it has happened. That's a real picture of a real vessel that rusted all the way through. Offshore structures, they're very hard to maintain. They tend to corrode, so they look like buckets of rust in many cases. So this is general rust. Here you see a specific form of corrosion. It's caused by cavitation. We're going to touch on that later on. So I don't know how familiar you are with cavitation, but when you get moving liquids, moving water around a metallic surface, you get a phenomenon called cavitation, which can seriously destroy the coating, and then the underlying metal rapidly corrodes. Here we have chemical corrosion in these next three. This is the inside of a scrubber recycle tank. Again, we're going to talk more about scrubbers later on, so if any of you are not familiar with scrubbers, we'll cover that. But you see what happens. It's a chemical reaction. They have very acidic liquids that are taken out of the exhaust of a ship from heavy fuel. And these are recycled, these are put in a tank, and then they go through pipes. And if you use mild steel, which they often do, it tends to rapidly eat away the coating and then affect the underlying metal. Here you see it from the outside of a ship. This is taken by a diver. And the damage is actually at the point of causing a leak into the engine room, because the mild steel is corroded away, is eroded and corroded by the chemicals. The bottom examples are abrasion. This is an icebreaker, these first two pictures, And you can see what the ice does to the surface. It takes away the coating, and then the underlying steel becomes badly pitted. And this is typical in ice breaking conditions, ice going conditions. Here we have the deck of a ro-ro ship. They're used to having heavy vehicle traffic on it, and you can see here the deck is very badly eaten away. So these are the areas we're going to be looking at. And again, I'm not trying to cover the whole subject. I'm giving you specific areas that you are going to run into if you're on ships, building ships, repairing ships, and so on down the line. Cost of marine corrosion is between $50 and $80 billion annually. That's the general accepted figure. Whether it's accurate or not, I don't know, but you can tell it's an awful lot of money spent on tackling corrosion. So this is from the Marine Industry magazine. It has been estimated that the total cost of marine corrosion worldwide is between 50 to 80 billion every year, dollars, USD. The coatings industry accounts for 40% of the total direct cost, which is a good deal. And you'd think that that amount of money would have solved the problem, but it really hasn't. Theory versus practice. There's a lot of theory and literature on the physics and chemistry of corrosion. You'll find books and books and books and tons of information and courses and lessons, and you may have had some or you may be getting some. There's a lot of classification, types of corrosion, and fine distinctions, one type or another, and I'm not going to cover that at all. Because for the ship owner and operator, or the fleet manager, the superintendent, the dry dock manager, the captain and officers, engineers, crew, and the naval architect and shipbuilders, all those involved in building, operating, and maintaining ships and offshore assets and their whole support infrastructures, it really is a practical matter. Their concerns are, well, how do I prevent it? How do I deal with it? You know, in dry dock, they see the time it takes to repair and repaint from a damaged rudder or damaged hull. There's the expense involved in dealing with corrosion. These are the things that you're going to be up against. So they're also aware of the danger to the safety of the ship and crew. They need practical solutions. And that's what we're looking at in this seminar. Okay, so far? Am I coming through clearly? You hearing me and so on?
Loud and clear, sir.
Okay, great. We'll continue. Oh, we're going to have a question period at the end, by the way, but if anything, if anybody's really held up and can't go any further without asking a question, try and attract my attention and I'll answer it as we go. Okay. So the first type, we're going to look at four types of corrosion. The first one is it's called general corrosion. It's known as general attack corrosion, uniform corrosion, or more usually rust. And here's this example here. The second one we're going to look at is cavitation damage resulting in erosion and corrosion. We're going to take up each of these separately. Third one is chemical corrosion. And the last one is impact, abrasion, and wear. In itself, it's not corrosion, but it leads to corrosion. Okay, so the first one, general corrosion, which we call rust. Steel, which is the most common material for shipbuilding and any offshore structure and so on, is made from iron ore through a process which involves an awful lot of heat and chemical reactions. At the end of all of that, you get steel, mild steel. It's the most common building material for ships. It's the cheapest. It's strong. It's tough. It's easy to make and so on. However, it's not in its original stable state. Steel is in a state of tension, and it's trying all the time to revert to its original state, which is just plain old iron ore. And when you see the rust here in that color, that is the color of iron ore. That is some steel that's successfully managed to return to its original state. Okay? And this results in wastage and weakening of the ships and the structures. The sea is one of the most corrosive environments on Earth. You get a combination of air, water, and salt, which are deadly. They cause unprotected steel in particular to rust very rapidly. It's a chemical and an electrochemical reaction, and that's all I'm going to say about the actual cause of it. You've got steel. It's trying to revert to its original stable state, which is iron ore, and get out of this artificial stage, if you like, of being steel. And in doing so, you can get serious damage to your structures, which are built from steel. The chemical and electrochemical reaction is not really important in the detail. It's all available, and I'm sure you've been exposed to it. You may know all about it. You may know more about it than I do, but we're not going to cover it here. Obviously, this is a known phenomena, and it takes up a lot of people's time. And as we've seen, it takes up a lot of people's money to try and prevent it, to try and deal with it when it comes up. You know, you're building a 400-meter offshore production and storage unit for LNG or something like that. And it's expected to stay offshore for 25 to 40 years. And you're building it out of material that you know is prone to corrosion. And you know that if it does corrode, that thing is going to be shut down. And the cost of shutting a vessel like that down for even a day is unbelievable. It's really high. So every attempt is made to prevent that corrosion from occurring at all. And if it does occur, if it is noted, then to be able to prevent it from spreading, from getting worse. But these are the methods in general use, and probably you're familiar with them. There's the design of the hull itself or the structure of the tank to reduce corrosion and to maintain strength in the face of corrosion. So that's a subject for naval architects to deal with. In fact, most of these are. There's a choice of materials. You know, ideally, maybe you build a whole ship out of stainless steel, but the prohibitive cost and the other factors that come into play with stainless steel make that not a choice. It's just not done. But you can choose materials. You can choose materials in certain parts of the ship. You can add stainless steel belts inside thruster tunnels. You can fortify a rudder with, you know, and so on. So choice of materials is another possible approach. There are general protective coatings, and epoxy is quite common. The idea is you coat the steel, and it prevents the water, the salt water in the air from getting to it, so it won't rust. Should work, should be fine if you can do it properly. There's a lot of technology around cathodic protection systems. The two main types, you either stick sacrificial anodes on the hull or the part of the ship, and they basically, a sacrificial anode is a chunk of metal which is of a lower, it's less noble than the steel of the hull. So if there's going to be corrosion, it's going to happen first to the sacrificial anodes. That's the theory. And it actually works. You see these zinc anodes on ships, and they come in and they're all, see if I can show you one here. No, I don't have them in that picture. Well, we'll come to that later on. But this is common. Zinc sacrificial anodes are common. And there's also another system whereby there's an electrical current is put into cathodes on the hull of the ship. And it's designed to prevent the electrical currents which flow around the hull from affecting the main hull. They tend to be attracted to or affect the impressed current terminal. So this is another method that's used, and it's designed to reduce the effect of corrosion. There are corrosion inhibitors. Zinc is quite common, and they're put on as part of the protective coating, and they're designed to stop the corrosion from happening or at least slow it down. Another approach is to use thicker plating. In other words, you compensate when you design your ship by adding however many millimeters of steel everywhere to compensate for the expected loss of steel due to corrosion. So these are all different approaches. They're the main ones. Often you'll see a combination of them used, and they're usually used with the viewpoint of, okay, how do we mitigate the corrosion? Not how do we prevent corrosion? How do we slow it down? How do we reduce its effects? Mitigate. So those measures are in use, and you're going to run into them everywhere. And there's many providers of these different ideas. Naval architects are taught how to use them. There's lots of theory, and they all have validity. However, there's a point of breakdown, which is common to all corrosion, which is the coating. If your coating starts to break down for one or more of a number of reasons, the underlying steel is exposed, and then you start the long slide. Why would a coating break down? Well, it could be the wrong coating. It could be just an inefficient coating. It just doesn't do its job properly, even though it's put on. You know, you try some cheap coating that just to cover it and say you've done it, and you haven't really coated the hull properly. It can be poor preparation, and it very often is, because if you don't prepare the underlying steel thoroughly and properly, it doesn't matter how good the coating is, it's not going to last. It's going to come off. You're going to get delamination, the paint is going to come loose, moisture is going to go through and spread, and you're going to lose your protection. Those are the main things. It could be, it's either a poor coating, or it's poor preparation, or it's just the wrong coating. When that happens, the cathodic protection system, here you see a sacrificial anode in place, and it's not really working, judging by the surrounding. As I say, these pictures are to make a point. Many of them are exaggerated, and you're not going to necessarily run into that situation every day. But here is a protective sacrificial anode supposed to be protecting the steel from rust, and it's not working. Cathodic protection systems are not up to fully preventing corrosion. They'll help. Corrosion inhibitors may inhibit, but they don't prevent corrosion. And under these circumstances, the sources combine and work together to accelerate the corrosion process. Some cases you get a very rapid progression of corrosion, which can be dangerous to the ship, the vessel. But it's a combination of these factors. It starts with, and the weakest link is the protective coating. That's the Achilles heel in corrosion protection, and it's very simple, and it's much more simple than you're going to see it stated in many cases, but it comes down to, did your coating protect the steel or or whatever it is, aluminium or GRP or whatever? Did it protect it properly, or did it not? Or did it give way after a while? And if you can deal with that, you're actually dealing with the problem at the point where it can be dealt with successfully. So protective coating, that's what we come down to. And again, I've got to remind you, this is from our viewpoint, from my viewpoint. It's not necessarily what you're going to hear from somebody else, but from our viewpoint, the coating is the weakest link, and the coating is the answer to solving it. So here's how we see the key to solving corrosion in general on ship's hulls and other parts of vessels and offshore structures in the coating. This is a semi-submersible. I'm going to tell you more about it later on. Semi-submersible that was converted to a rocket launch platform. And here you see a properly coated hull. It's got a coating on it designed to last. They needed 15 years out of dry dock, basically. So this coating was designed to last at least 15 years without the need for any repair, any repainting. But they happen to not use cathodic protection because they don't need it, because you've got a full insulation and seal of all the metal that prevents seawater, air, oxygen, chemicals, anything getting through to the steel. And I'm going to show you many examples, but basically From our point of view, the steel has to be fully coated and insulated against seawater, also biofouling because you get barnacles attaching, and barnacles will eat their way through many coatings. They penetrate, they pierce the surface, they break through the coating, and then your insulation is gone. So your coating has to prevent that from happening. It should be resistant to chemicals, any other corrosive elements with a tough, and it's tough, it's durable, it's impermeable, and it's impenetrable. It should remain intact for the life of the vessel or the structure, whatever that intended life is. And you also, because fouling accumulates always, it should be cleanable in the water. It also, from our point of view, should be entirely non-toxic. It should not put anything into the water which poisons the water or contaminates the sediment, which means non-toxic. That means that you can clean it in the water without harming the marine environment locally. So these are the factors that a really good solution to corrosion will take into account. I said I'd tell you about this one. Basically, they took here you see it on the right. It's a rig. No, it's an oil rig that was converted to be a rocket launch platform. So now Boeing and partners would use it. They'd take it down to the equator and launch a rocket to put a satellite into space. And it would happen every so often. There'd be a long gap in between. They tried to use, the second picture here, an anti-fouling coating. And after 5 years, they came into dry dock, and that's how it looked. As you see, it's gone. That's not protecting a hull. That's exposing a hull. They coated it with a different kind of coating. I'm going to give you the details of this type of coating later on. I'm trying not to make this a marketing and an advertising presentation, because it's not. It's actually a type of coating rather than a brand of coating that I'm going to tell you about. They would sail down to the equator, launch their satellite into space, sail back to Long Beach, California, and sit there for maybe months on end waiting for the next launch. They would accumulate very bad fouling, as you can see here. Now, with a poor coating, that will eat its way through. It will not stand up. The coating will not stand up to this level of fouling. They would get it cleaned when they were ready for their next launch. And as you can see here, this is the same coating. This has been cleaned it's 10 years on. It's been cleaned many times. The fouling has been removed, and it's very heavy fouling. And the coating is in its original condition, and they could sail again and get good fuel consumption. So this worked for them. I'm going to actually tell you what the superintendent of that particular vessel had to say about this type of coating. His name's Jan Bakker. He's a senior superintendent with Williamson, a very experienced superintendent. And he'd had experience with this type of coating for several years before he made this statement. He said the main reason we chose this particular coating for the hull was to avoid the penetration through the paint by the fouling and to protect the hull. And he'd just seen it come back from one of its trips. He said, I saw that it's not penetrating. The fouling wasn't penetrating. It looks good. And then he made some general comments, because he was very aware of the industry in general. He said there were some jackup rigs ahead of us in dry dock. I saw how much steel they had to change due to a poorly protected hull. What they do is just put a lot of anodes on and sit there. And then they have to go into dry dock and change a lot of steel instead of putting the coating on the hull to begin with. One of them had been in dry dock for 6 or 7 months changing steel. That's a lot of money. They can get rid of all their anodes and all the rest of it and put this coating on. That would be a big benefit. So this is a common situation in the industry where really, due to corrosion, there's a lot of steel replacement is required. And he's saying from his experience that the solution would be to use this type of coating, throw away the anodes, and they'd be fine. By the way, I should tell you, I'm going to make this presentation available in PDF form to anybody who wants it. So you don't have to worry too much about, what's on here you will have, and probably some other literature as well, just in case you're worried about taking notes or forgetting stuff or whatever. This will be made available to everybody. Okay, now we're going to look at a cruise ship. We looked at a specific offshore type of vessel. This is a cruise ship now. This one had been in service for 7 years with a conventional anti-fouling paint scheme, which is, I don't have to particularly go into details of what that is, but it's a number of different types of coatings, starting off with a primer and usually some kind of epoxy corrosion prevention scheme, and then mid coats, and then on top of that, they put a couple of coats of anti-fouling, which is designed to gradually leach away while the ship sails and is toxic so that it prevents biofouling from attaching through its toxicity. It's a way of keeping fouling off a hull. They've been using that for 7 years. Here they are in dry dock. Their hull is very, very corroded. It's very poor protection. They were not happy. So it was recoated. Here you see it being blasted. All that coating is being blasted off, and the surface is being prepared, and it's being recoated with a different type of coating designed to last. This kind of coating does not have any anti-fouling property, so it fouls. So you have to clean it. They did. They cleaned it regularly, as much as they were sailing in hot water. So as often as 6 to 8 weeks, they cleaned the hull, preferably when it's only at the level of a slime or light weed, not a heavy fouling, because then you get the maximum fuel efficiency. If you clean it at about that stage, it cleans very easily. Each time you clean it, it actually gets a little bit smoother. You do not damage the coating, does not damage the environment. And here it is in dry dock 5 years later. And you can see this hull is in nice condition. It's not corroded. It's just been washed off in dry dock. Actually, the officers and crew of these ships nicknamed this type of coating the wash and go coating, because they would arrive in dry dock, it would get washed down, they'd touch up any mechanical damage, a few liters of paint to touch up the mechanical damage, and that would be that. They could sail, as opposed to the usual situation in dry dock, which is more like this, where you have to recoat every 2.5 or 5 years or whatever it is. The whole coating has to be either patched up and the top coat replaced, or you have to redo the whole coating. So this is a different approach. It stays on for the life of the vessel. They also, by the way, noted that they had an increase in fuel efficiency with this coating system, that coating and that cleaning, 10% increase in fuel efficiency. And if you take their annual fuel bill and take 10% of that, that's a chunk of cash. So that saved them a lot of money. They had to pay for the cleaning, of course, but the cost of the cleaning was minimal compared to what they saved on the fuel. Added advantage was this kind of coating, it was completely non-toxic. So they were not damaging, contaminating the environment in the ports that they would sail to. They gained PR value from it of, hey, we're a completely green ship. When we go to Aruba or something and we dock for 3 days, we do not emit any chemicals into the water. But you see, they solved their corrosion and other problems at the same time. Many years on, they still had the same coating on. It was the original. They didn't change it. Okay, so that was general corrosion rust, the first one of the 4 we're going to cover, right? That's the end of that so far. We're going to talk now about cavitation damage. It's a special case of corrosion. I don't know if you know about cavitation or not. I expect you do if you've studied it, the physics of it and so on. You get turbulent fluids, like behind a propeller, for example, create cavities or bubbles in the water. When these hit the steel surface, they explode, or they implode actually. And they implode with extremely high temperatures and pressures. It's a very strange phenomenon, but there it is. You see the results here. These bubbles, which is all that is, have damaged, they've completely removed the hull coating, then they've pitted the steel, and the steel is corroding like crazy underneath. And that's after 5 years. with regular hull coating. And you see they've even got a sacrificial anode here, and it hasn't helped it. Here's your damage. Very often a ship like that has to come into dry dock, and they sometimes have to take the rudder off completely, but at least they have to do welding on the surface to repair it, patch it up. It gets holes in it. It's quite a nuisance. It's quite a headache to many kinds of ships. These rudders are of large container ships, which tend to suffer the most. They have high speeds, they have fast, big propellers, and they have big rudders, and this is what happens. Another area that's affected by cavitation is the inside of the thruster tunnel. In here, you have the thruster propeller turning around, creating the same kind of turbulent motion in the fluid. And even though they frequently put a stainless steel belt inside there to protect it, the corrosion occurs anyway. The cavitation will damage the coating, and then the salt water goes to work and you get corrosion. So that's another area that often needs to be repaired. Here you see a rudder of a ship. It's actually, the ship is the Seaspan New York. It's since changed its name, but this was 5 years since its last dry docking, came into dry dock. And you can see what the cavitation has done to the rudder. It's very damaged. And corrosion is setting in, and that rudder required quite a bit of repair. So, conventional hull coatings, what normally happens is, they'll just put the regular hull coating on here. It doesn't protect it at all. It just is not up to it. Again, I'll show you another couple of examples of how that goes. But it just doesn't protect the steel. The coating gets taken off quite quickly, and then the underlying steel starts to get pitted with the damage. If this were adequately protected, if it could be, you would not get any of that. The coating actually would protect the steel, as we covered in the earlier point about the weakest link. The weakest link in the spiral begins with a protective coating. Well, it's no different for cavitation. There is a type of coating that will protect a rudder and other running gear completely from that damage. And it has been found to be effective. It's a glass platelet reinforced vinyl ester protective coating. Again, I'm going to go into this in more detail later on, because it's the general type of coating that is extremely useful for protecting any steel from corrosion. Here we're talking about its use for protecting rudders, quart nozzles, azimuth thrusters, thruster tunnels, stabilizer fins, other parts of the vessel, steel, aluminum, or GRP that are likely to suffer from cavitation. I'm not going to go into detail on the coating here because I'm going to cover it in detail later on, what it consists of. But basically, it's very tough, and these forces of cavitation are resisted by the coating to the point that they don't cause the damage. Here's that same rudder. And this is a practical example. This is a practical seminar. Same rudder. Here it is, that picture that I showed you already. It had come into dry dock, and this is what they were confronted with. And this is normal for a big ship. The rudder is frequently like that when they come in after 5 years. They have to repair it. They can't sail again like that. It's actually taken away part of the plating here. If you look further down at the bottom of this rudder, along this part here, on this one, you'd see that there's damage to the wells. There's probably holes here, leading edge. It's in trouble. Okay, so this was coated. It was repaired in that dry docking, and it was coated with this coating. And here it is 10 years after that coating was applied. It's not been repainted. It's not even been touched up. It does not use cathodic protection. There's no anodes. You can see this is the normal hull coating, which is in serious trouble. This has just been washed off in dry dock, and it's 10 years on. That's how it looks. The proof of the pudding is in the eating, right? Here's the 10-year result with this particular type of coating, which I showed you here. It's in use by more and more major shipping companies are finding out about it, and they're one by one painting their rudders with this paint because it saves them an awful lot of trouble in dry dock. Another specific case study, this was the Israeli Navy. They built these corvettes. They bought these corvettes to protect their offshore assets in the Mediterranean. They're German built. I'm going to read to you what Commander Hakoun said about it. He was the guy over the project and determining the right coating to use and so on. He said, we were originally using the same standard anti-fouling paint system for the rudders that was on the rest of the underwater hull. The primer layers were epoxy based and the top layers were the active anti-fouling system. Here's the second picture. You see the red is that he's describing. The white is the underlying epoxy-based primer layers. He says, after the sea trials of the first ship, the Megan, we docked her. And this picture is from that docking. We witnessed severe damage of the coating on the rudder blades. This is after the sea trials, mind you, right? It's not been sailing any length of time. The damage was shocking to everyone, from the shipyard designers to the rudder blade designers. The reason for the damage was very clear: cavitation phenomenon. The real surprise was that the cavitation was so aggressive that damage to the steel was about to occur after only a few days of sea trials. This picture here shows the rudder after a few days of sea trials with regular anti-fouling coating on it. It's gone all the way down to the metal in places. You can see that. It started to rust. 3 or 4 days later, they were so concerned about their rudders that they put a video camera just to make sure their rudder was still there because of the cavitation. Anyway, they said, we received a recommendation from Becker Marine Company, who designed the rudder blades. You probably know Becker. They're a very famous German manufacturer of running gear and so on, propellers, stuff like that. They said the most efficient way they saw of handling the situation was to protect the rudder with a durable coating for cavitation. Based on their experience, they said this particular coating system showed durability and resistance to cavitation. I've taken the names out because, as I said, I'm not advertising. Our hope is that the use of this coating will enable us to maintain our current dry dock maintenance schedule. I'm very optimistic. This is that same rudder on the same ship, same conditions, after 6 months of sailing, and it's been washed off in dry dock. And it's undamaged. They did coat it very well, by the way. Not only did they prepare it properly, they put on 2 coats of this coating, but they also did a stripe coat over the wells, which means an additional coat of paint goes on in between coats for the areas that are likely to suffer damage. Anyway, here it is 6 months later, and it's in good condition. It's in fine condition. He's been in touch with us since, and they are not having a problem with the coating. So another example of practical solution. Greek shipping company, Pleiades, this is another example. We were experiencing heavy cavitation of the rudder blades as well as cavitation damage on the propeller nozzle. This is the nozzle on all our vessels. With the Xanthos, which these pictures are of, after high pressure washing, the rudder blade and the propeller nozzle were in immaculate condition 7 years after the coating was applied. This is this picture here. Fantastic. Having a rudder and nozzle in good condition from a typical dry dock of 10 days, you save 1 day. Roughly speaking, 10 to 15% time saved from the total dry dock. The market right now is $15,000 to $20,000 per day for that kind of ship. So you can save $15,000 to $20,000 off the dry dock just for 1 off-hire day. That's without taking into account the additional labor, the cost. I mean, this one probably had to be welded. You can see they'd have to repair the surface. And that's for that type of ship. It would vary. How much you save will vary with the type of ship. Some ships off-hire time is much, much higher than that. So this is 7 years after it was coated. Here's where it was coated. 7 years later, it was washed off, and that's how it looked. Okay, so this is how to prevent, solve cavitation damage. The parts of the ship that need this special kind of protection include the bulbous bow. For many kinds of ships, particularly if you're sailing in ice or something like that, the bulbous bow suffers badly. The draft marks sounds like a detail, but it's really important to have draft marks that you can see. And the coating tends to be taken away on regular coatings. Inside the thruster tunnels, we've talked about already, there's an area that's very subject to cavitation. Stabilizer fins, if you've got them. C-chess, the grating and so on, it can easily lose its coating. Scrubber outlet areas. We're going to talk more about scrubbers. I presume you know what scrubbers are, but just in case, it's the exhaust gas cleaning system that's used if a ship is sailing with heavy fuel rather than low sulfur fuel. It's much cheaper fuel, but in order to meet IMO regulations, they have to clean a lot of the harmful exhaust out before it goes into the atmosphere. That's called a scrubber, the device that does that. There's different types of scrubbers. Some of them keep the effluent inside the ship, others just shove it straight out into the sea. So because of that, it's very acidic. The effluent from the scrubber is extremely acidic, and it takes away the coating, not just inside, but also the surrounding hull area. So that's another area that needs protection. Any energy saving devices near the propeller tend to suffer from cavitation. You can see here, they've got these extra anodes here to try and protect it. But the coating will do as well as instead. The propeller itself is often subject to erosion and can use extra protection. And then the rudder is the big item. Also, for some ships, the boot top area here, or the ice belt for an ice-going ship, but the boot top, it tends to suffer abrasion mostly, and it can use a much tougher coating to protect it from the tugs pushing against the side, you know, the lock walls and that kind of thing, depending on where the ship sails. So here you see all of these parts of the ship that if you don't protect them thoroughly, you're going to pay for it in dry dock. And could be worse, you know, you could lose your rudder entirely at sea, and that's not a very propitious situation for sailors. All right. So that was cavitation. I hope that was clear. We're now going on to chemical corrosion. It's different. It's not the metal rusting directly, but the chemicals, what they do is they remove the protective coating. They just chew their way through it, as in rodents, and the protective coating is gone. So now the salt water can seriously have its day with the underlying steel, and it rusts. So it could be either, it's usually an acid or an alkali, direct contact with the steel or other material, and it takes away the coating. Many protective coatings, such as conventional anti-fouling paints and silicone coatings, are not chemically resistant. So the chemicals will eat their way through quickly. Here you see, let's see, this is a tank. I'm not sure what kind of tank this is. I think it's the inside of perhaps even a sewage tank, I'm not sure. But obviously the chemicals involved are very corrosive, and this is the effect. Here you see the overboard pipe of a scrubber system. That's this little pipe here, right? Seen by a diver from the sea side, and the paint has gone. The steel is in jeopardy. With too much corrosion, you actually get the seam here, the well seam between the pipe and the hull can be eaten away, and water will start to enter the ship. So you see water coming into the engine room from near the overboard pipe, which is not a nice sight. Here you see the inside of a scrubber recycle tank. It's hard to tell what it is because it's been so badly damaged by the acid, but the actual frame is gone. I'm going to tell you a little bit more about this specific one later on. But you get the idea. This is chemical corrosion at work. If you protect these areas with a coating that is resistant to chemical corrosion, none of this will happen. Here you see scrubber outlet pipes. They're being coated with a special coating before they're installed, so that when they go on the ship, like here, they've been put in on the inside to replace an existing one that got eaten up by corrosion. But when they go in, they won't suffer the same damage. It'll actually be protected against that acid. So you can put as much acid as you want out of this pipe, and it will not get through to the metal. The coating protects it. Here's the outside areas of the hull surrounding the scrubber outlet, which normally with regular anti-fouling coating or silicone or whatever would just disappear, has been protected with a special kind of coating that protects it from that corrosion. And that'll come into dry dock. It won't look as shiny, but the paint will all be on. It will not have been taken away. And here you see the inside of a recycle tank, again, protected with a proper coating. So this is another type of corrosion, and the protection again goes back to the type of coating. You could convert this tank to stainless steel if you wanted to. It would be very expensive, and you would still have areas where there would be a problem. So if you can get a protective coating that'll protect the mild steel, you're better off in the long run. Okay, so this is that particular tank that I've been showing you pictures of. It was sort of a bit notorious because of the change that occurred as a result of applying the correct coating. But here it's how it came into dry dock, an absolute disaster. It was reconstructed, it was rebuilt, new plates, new metal, and prepared and then coated, special coating. Thoroughly, the entire interior, and the pipe as well was also coated with the same kind of coating. This is the first layer. It was then a second layer was put on, which was red. And the outside of the ship, around the same ship, around the outlet was also coated. Here you see it's protected with this special kind of coating. Came into dry dock. When was it? Okay, this is 2 years after it was applied. And this is how it looked before. This is how it looks after 2 years. There's no steel showing through at all. I mean, okay, the paint has lost its shine. There is no damage to the metal. So what's the reaction in the shipyard? Says a lot. The project manager of ZEME, which is a energy marine environmental technology company, was extremely satisfied with the performance of the coating. He was overseeing this application. The shipyard paint supervisor had never seen a coating in such good condition in a recycle tank. He said the coating is looking fresh after cleaning. No hot work is needed before painting, and only several touch-ups are needed with minimal paint work. He'd never seen that before. But it shows that it can be done. You can protect steel from chemical corrosion and subsequent further corrosion. So that's chemical. And it can apply in different situations, different types of tanks that are with corrosive chemicals and so on. They can all be well protected. And now we come to number 4. This is impact abrasion and wear, which we mentioned up. Where was it? Here, right? One of the last of the 4 that we're going to look at. It's very common. It's very widespread. The results are a headache to ship owners, to dry dock managers, to naval architects, to you in the future if you don't know how to deal with it. This is a headache. This is an ice-going ship here. Ice is impact. These icebreakers hit into the ice. The ice has sometimes got rocks and lava in it or sand. It's extremely abrasive. You can't get worse than that. And most coatings are shredded when the ship goes in the ice, even though there are special ice abrasion resistant classified coatings, which this ship had on, by the way. So that's ice. And these 2 are decks. And I'm going to cover ice and decks mainly, but it applies to other types of abrasion as well. Just, the constant wear of workboats coming up against a floating wind structure, for example, will wear away the polyurethane and the epoxy coating, and you'll start to get corrosion setting in. The problem with wearing away the coating is, well, it looks horrible, but that's not the main thing. The main thing is you've now exposed your steel. Now the salt water can go to town and this will just corrode away. So there's different types of abrasion. You know, this, for example, this deck here has heavy vehicle traffic up and down all the time, and sometimes in the snow and ice and so on. There's just sheer impact with the ice. These ice breakers have, I don't know if you know how they work, but they ram the ice forwards and they go backwards, and they come into the ice backwards and forwards, and they ram and they hit the ice hard. Ice is hard. Ice is not gentle with the ship hull. So this damages the coating if it's not tough enough, exposes the underlying steel. Okay, let's have a look at some specifics here. This is a company called Interscan. They have a tramp steamers that particularly trade in the Baltic. Half the year it's in ice, half the year it's not. This is how one of their ships used to come into dry dock. They just put a cheap anti-fouling coating on for the simple reason that they knew they were going to have to replace it every dry dock. So they didn't spend a lot of money on paint, but this was the effect of a year's trading in one of these ships. And that rust is taking away steel. It's not just the paint that looks so bad. The rust is also having an effect. You're losing some steel. Eventually you will have to replace steel or scrap the ship. You reduce the duration of the ship. So that's how they come in every year to dry dock until they found this other kind of coating that they decided to try. It's more expensive for them. They had to completely blast their hull down to bare steel. They had to prepare it properly, and then they put on this other kind of coating. This is that same ship after 3 years. And it's just been washed off in dry dock. It's not being painted. There's no touch-ups involved. It's a huge difference. You can see that hull is completely protected still. There's no exposed steel. Maybe tiny little spot there you can see that got damaged by ice, which is very simple to repair because
Mr.
this
David,
coating. Yes.
Mr. David, sorry for interruption. Your slide is not moving.
Say that again.
Your slide's not moving.
The slide's not moving. It's not changing from that to that?
It's only. Yeah, it's not changing.
Really? Huh.
3 chemical corrosion, it's there. Yeah, now it's moving.
How's that? Does that show you impact
Thank you.
abrasion and wear? Did that change or not?
Yeah, now it's changing.
And that one? Okay. Well, let me know if it happens again, and we'll stop. Okay. Did you follow this, or did I leave you behind somewhere?
Yeah, go ahead. Yeah, follow.
It's okay to go ahead. All right. Good. You got the story on this one, did you? This Baltic trader? All right. Did that change?
Yes, no change.
Okay. All right, good. So this is an example of ice. This is FedNav's Umiak 1. It's the world's most powerful non-nuclear ice-breaking cargo ship. It sails in Canada. Every year it has to break ice like that to get, I think it's nickel they bring back from the mine. Anyway, it carries ore, metal ore from a mine off the coast of Canada. This picture on the left shows the hull with the original coating. Full protection, you need a high proportion of large aspect ratio glass platelets. You see these here? Their surface area is much greater than their height. That's the large aspect ratio factor. And the reason for that is that they overlap in the resin. And because they overlap, there's no clear path for liquid or vapor or anything to get through. It actually will protect the hull if it's thick enough and if there's enough glass to provide that protection. This is a high quality glass. It's a special kind of glass, and it's a vinyl ester coating. And I'll tell you more about vinyl ester in a second. So there are lots of glass flake coatings. They're not unusual. What are the variables? What makes one better than another? Because I'm going to tell you straight, this one here, this ship originally had, that original coating is, quote unquote, glass flake vinyl ester. So how come that glass flake vinyl ester didn't hold up and this glass flake vinyl ester did hold up? Well, that has to do with the variables. The variables of a glass flake coating are the type of resin used, the type of glass flake, how it's manufactured and what kind of glass, the size and aspect ratio of the flakes or the platelets. Prefer to call them platelets because flakes can easily be much too small. The relative proportion of the flakes to the resin. There needs to be enough glass in there to make it effective. The use of coupling or bonding agents to improve adhesion, very important. Internal adhesion within the coating, but also adhesion of the coating to the substrate, like the steel. So then you have the overall formula of the coating, taking all of these factors into account. Type of resin, type of glass flake, size, proportion, and bonding agents. Other variables are how thick do you put that coating on? How well prepared is the surface? What preparation of surface do you require? The application itself, you can get good and bad applications, it's not always the same. And then the maintenance of the coating during the life of the vessel. These are the variables that can make a ideal marine coating succeed or fail. Quick note on resins, because it's a key factor in this. The resins most commonly used in glass reinforced coatings include epoxies, polyesters, and vinyl esters. They are not the only types. You're going to run into other glass flake reinforced coatings, but I'm talking about the main ones in general, in more general use. Epoxies are widely used because they form a thick coating. They generally have good resistance to chemicals and corrosive substances, particularly alkalis. They're fairly easy to use. Polyesters are the cheapest, so sometimes they're used instead of epoxies to cut costs, but they're not the strongest. Then we have vinyl esters, which were developed as a way of combining the best qualities of the epoxies with so basically the simplicity and low cost of polyester combined with the thermal and mechanical properties of epoxy. Try to combine those two, and they came up with vinyl ester. Vinyl esters have properties superior to those of epoxies, particularly in terms of their inertness and their resistance to those chemicals which epoxies do not resist well, such as acids. Now, there's another factor with vinyl esters. If you put a coating like this on a ship, if it's brittle and hard, it will crack. When it cracks, porosity develops. The moisture gets through to the steel hull, and you've just blown your whole system. It doesn't work anymore. Epoxies tend to get brittle after a while, maybe several years, but they will become hard and brittle. And then, for example, if you tried to have one of those in the ice, the steel of the ship flexes with the ice. You hit ice, it flexes the steel, off goes your coating. It will delaminate, it will disbond if the coating is not flexible enough and adherent enough. So that's resins. We've talked about resins. I'm not going to go into too much detail on the glass, but not all glass is the same. There are different kinds of glass. There's high quality glass, it's more expensive. If you try to cut costs on the glass, you're going to end up with less of a durable, effective coating. In fact, any cost cutting in the preparation and application stage of materials, of labor, of everything else is going to come back and bite you over the years. You know, and if you're dealing with one of these offshore structures that are supposed to stay out there for 40 years and after 15 your coating goes, you've had it. I mean, it's impossible to repair without huge expense. So it's worth remembering, if you're ever in a position to determine the application of coating and the type of coating, that even if it seems more expensive, which some are, at the time, you must take into consideration life cycle costs. You must take into consideration the safety of crew down the line and so on. So be prepared not to go with the cheapest. Okay, so now I'm going to tell you about this particular coating that I've actually been referring to in all these examples so far. It's the same basic coating that was used here and here and almost the same coating that was used on the rudders and running gear, although there's a slight different proportion of glass to vinyl ester in that one. Makes it a bit tougher, which is why it's special for cavitation. But all of these, the same chemical corrosion, same coating, and abrasion resistance coating, ice going coating, the same. Okay, so I'm going to tell you a little bit about this type of coating. Here you see two layers of the same material. They're different colors because just to show you that it's applied in two different coats. That is 1,000 micron, 1 millimeter, 40 mil of coating applied to bare steel. It could also be aluminum or GRP, it doesn't matter. It's applied, there's no primer, there's no coating in between, there's no coating on top. It's just a millimeter thick vinyl ester with glass platelets in it. And there's about 300 glass platelets between the surface of the coating and the steel. If you apply 2 coats, you can go to 3 coats with this coating, with this paint. If you want a really long warranty, or you really want to be sure that 25 years later it's still all intact, you can put a 3rd coating on, particularly for an offshore type of structure that you really can't dry dock. So that's all you get. You get one type of coating. It's in 2 layers. It's applied first one, then the other, to build up a millimeter thick coating of vinyl ester with glass in it. Now, what does that mean? It means liquid cannot make its way through. It's absolutely non-porous. Maybe in 50 years, a few droplets would make their way through to the steel, but really it's as close to impermeable as you're going to get. It is chemically resistant to a very long list of chemicals, so it won't corrode. There's a few that you have to be careful with, but the majority of chemicals that are used in ships and on ships will not affect it at all. Biofouling will attach, but it sits on the surface. It does not penetrate. Remember with the with this chap here, the rocket launch guy, he said the main reason we chose the coating for the hull was to avoid the penetration through the paint by the fouling, because barnacles do, they chew through. This coating, they cannot chew through. They don't like it very much, but they will attach. And if you can clean them off, you can clean them off without leaving a trace. You can clean them off without damaging the coating at all. And because this coating is completely non-toxic, you can clean underwater without putting chemicals into the water, into the marine environment. So the environment's becoming more and more important, including the underwater environment. Many people, many ports are very sensitive to what goes into their water. This coating will not affect it. It will not contaminate. It has, interestingly enough, this coating is classified ice abrasion resistant by classification societies, Polar Code 1 to Polar Code 7. What does that mean? It means you can sail a ship protected with this coating in any sea, in any season, and it will have classification okay from a coating point of view. It also means that you can reduce the thickness of the steel on an ice-going ship by up to 3.5 millimeters if you use this coating. So It's tough. And even for a ship that isn't sailing in ice at all, you've got the security of knowing that this is a tough coating on that hull. It's not going to be damaged easily. Of course, you can. You can damage it if you mishandle your anchor chain. And yes, metal against metal, no coating is going to stand up to it. But it's very tough compared to most. And here's the abrasion resistant factor there in that last picture. So that's the coating. That's what it is. It's high aspect ratio, special glass platelets in vinyl ester with bonding agents to make it stick. It's 1 millimeter to 1.5 millimeters thick, which is thicker than most coatings go on. The epoxy is usually applied at about 500, half of that. So it's thick, you're putting more paint on, and it's designed to last, 25, 40 years, the life of the vessel. Here's the application details. I don't know if this is all going to make sense to you all. I don't know how much you've been taught about paint, but I'll explain it in fairly simple terms for anybody who doesn't know much about paint application. The first thing that you require. Yes. Yeah.
Excuse me. Can you have 10 minutes break?
Can I do what?
No, you want to take 10 minutes break, then we will come back again.
A break, yes. How long?
10 minutes, 10 minutes.
10 minutes. I'll be back. I'll be here in 10 minutes. Good. I need a cup of coffee. Have a good break.
Yeah, please.
Okay, guys. Yeah.
Now we have arranged the key. Please come back after 10 minutes. And we have movies on how they are doing the underwater painting and other things.
Hello.
David?
Yes. Was it a good break?
Yeah, we can start now.
Okay, cool.
Thank you for waiting.
I've switched my location to the shipyard for this part.
Yes.
All right. Anything I need to recap or any major questions so far, or shall I just continue? There's a little more.
Maybe after completing, we will ask you the questions from the
Okay,
students.
All right. Well, we were just about to start on application. How many people are in that room, would you say? Great. Wonderful. I'm just letting them settle.
They are marine engineering students, undergraduate.
Say that again. How many?
They are marine engineering students from undergraduate.
Okay. Good. Okay. So we'll talk about application of this type of coating, shall we? Just a few more coming in. All right. And you can hear me okay?
Yes, yes, yeah.
Good. All right. So the first thing that you need to do to get this kind of result of preventing corrosion with the right kind of coating is you've got to prepare the surface properly. This means, in this case, with this kind of coating, you need to have a rough surface. It's got to be 75 microns, which is 3 mil roughness. And this is very important. Without that roughness, it will not last. And then the next part of it is it's got to be clean. So there's a scale of cleanliness. This is the Swedish scale. And there's a condition called near white steel, 2.5 SA, which means it's not got any rust on the surface. It's not got any grease or oil or chemicals. It's very clean. Now you're ready to apply. The application is very simple. It's no special equipment. It's the normal shipyard paint spray equipment. It's a single nozzle, airless spray. There are some coatings, like for example, solvent-free epoxy, where you need to have two paint heads and they've got to be heated and the conditions are very important. It gets complicated. With this, it's very simple. You just use your regular single feed airless spray. You put on the first coat to a dry film thickness of 500 micron, 20 mil. I don't know if do you use micron or do you use mil in India? What's the usual measurement? Metric? Metric. Okay, so 500 microns. The first coat goes on. That's quite thick. That's actually as thick as most coatings are total or thicker. It does not run. It's easy to apply. And then you have a 3-hour wait period. And then you're ready to put on your second coat, which is quite quick. The other side of it is that you don't have to put it on after 3 hours. You can wait 3 days. You can wait 3 weeks. This is very handy when you're new building a ship, because usually the ship is constructed in blocks, which are then, and they can be at different shipyards, and then taken to a dry dock to assemble. And then the joints are welded up and the ship is finished. With this coating, you can put on the first coat in the block stage. In other words, you can build a block and coat it. And then you can bring all the blocks into the dry dock, put the ship together, weld up your erection joints, which obviously burns the coating at the edges. And then you just have to prepare that little section where the erection joint is, put on a first coat there, and then you can put on the final coat. With epoxies, it's a very tricky overcoat time. You've got to overcoat it at the exact right time, and the first coat has to be slightly tacky when you put the second coat on, or it doesn't bond properly. With vinyl ester, you don't have those problems at all. You can put it on after 3 hours, you can put it on after 3 days, you can put it on after 3 weeks without re-preparing. Very useful for shipbuilding, particularly. The total dry film thickness needs to be at least 1,000 micron. You can put on a third coat, as I mentioned before, if you want an extra long warranty, but 1,000 is sufficient for most purposes. The conditions for application, the humidity needs to be 85% or less. And the surface temperature of the ship hull or whatever has to be between 0 and 60 degrees, which is quite a wide window. It needs to be 3 degrees above the dew point or more. Otherwise, you get condensation, which affects the application. But that's it. It's not very stringent requirements. Shipyards are quite used to that. And then there needs to be a qualified coatings inspector who's familiar with the coating there present. As you can see here, he's checking the roughness of the preparation to make sure it's properly prepared. And then he will guide the applicators to make sure they know what they're doing and they apply it properly. And finally, he will measure the thickness. Actually, he'll measure the thickness after the first coat. And if there are areas that are a bit low, you'll mark them so that they can be built up on the second coat, so that the final dry film thickness of the whole hull or area, deck, rudder, is at least 1,000 micron. And that's it. That's all there is to it. So I'm going to summarize and then we'll get into questions. Basically, we've covered some types of marine corrosion, the ones that are most commonly encountered, I would say. Certainly the ones that we encounter the most, that people need solutions for, from a practical point of view. And you'll note that the solution to each of these situations lies in the coating. I warned you before that I'm talking to you from the viewpoint of a coatings company, and a disruptive coatings company at that. And you will get different viewpoints. So don't take my word as anything other than what we've experienced and how we see it. But we've solved all these problems from the coating point of view with the right coating properly applied. The best coating that we found is a vinyl ester reinforced with high aspect ratio, high quality glass platelets. This is the one that's been used in every example I've given you. It needs to be applied to a dry film thickness of 1,000 or more micron thick. The coating, if the ingredients are correctly monitored, is completely non-toxic to marine life. It's inert. It does not put anything into the water. It does not put chemicals, biocides, heavy metals, PFAS, any of these things. Nothing goes into the water, which is friendly to any environment, you know, because you get these chemicals leaching off of ships and they can damage coral reefs. They can contaminate sediment in ports to the point that you get dead zones. It's just not good policy to poison our oceans. They don't go on forever. So a non-toxic coating is of value from that point of view. This coating is long lasting. It's intended to last the life of the vessel. And here it's a break from the usual business model of the coatings industry, which is repeat business. Put a coating on and then put it on again after 2.5 or 5 years. And again after another 2.5 or 5 years. It's called a repeat business model. You make your money, it's a commercial thing. You make your money on selling the same product to the same company again. It doesn't have to be that way. You can make a coating, and any of the major companies could make a coating that lasts the life of the vessel. It's not that difficult to do. And then you don't, from a commercial point of view, you don't make your money on repeat business. You make your money on first-time coatings. There's plenty of ships out there. There's plenty of ships being built. They all need to be well protected. So anyway, it's possible to protect it for the life of the vessel. It needs to be abrasion resistant because there's always going to be some kind of abrasion. Chemical resistant, particularly where there's a chemical situation involved. This coating can be cleaned in the water aggressively with heavy fouling as often as needed to remove the biofouling. And I showed you some of that up wherever it was. Here, you see this coating here. It's 10 years after it was applied, and it's been cleaned many times because it fouled many times. So that's a key factor. Underwater cleaning is not necessarily always popular, but it's very frequently done, usually because anti-fouling will not keep a vessel free of fouling in between dry docking, and it has to be cleaned at some point. From a fuel efficiency point of view. So cleaning is important from a fuel efficiency point of view. If you can do that cleaning without damaging the coating, without damaging the environment, you're ahead. Properly applied, this can be an end to marine corrosion as a big problem. Obviously, there'll be details, you know, you'll have to solve this one and that one and the other one. But overall, this has the potential of solving the marine corrosion problem that we discussed at the beginning completely. It sounds simple. It is simple. Sometimes the best solutions are simple, you know, they don't have to be really complex in order to solve it. And so far, in all these cases that I've shown you, the problem was solved. There is supplementary information after we do the questions and so on. I'm very happy to have each of you have a digital copy of the Corrosion Handbook and a white paper called Conquering Corrosion in Offshore Vessels. Although it says offshore, it actually has quite a lot of it is applicable to all corrosion as discussed. There's a book called Surface Treated Composites White Book, which I don't have in digital form, but I'd be happy to send some copies to the university so that you have it in your library and so on. And there we are, ready for questions. I guess I should stop presenting. Huh? Let me see how I stop presenting.
Thank you, Mr. David. Now, it's open for discussion. Any questions from the students? Should ask some questions. Yes, you already read this. You have one chapter, no? I think it's corrosion. You have to have some doubt. No questions?
Sir, can
Yes.
we rubber coating on hull of a ship like submarines have?
Can it work on a submarine? Is that your question?
Can we use rubber coating on hulls of ships like submarines have? Like submarines have rubber coating on outside. So can we use rubber coating on ships as well?
Yes.
Will it affect?
If I understand, did I understand? I'm not sure I really heard all of your question. I'm sorry. The audio is a little bit not clear. Try again.
Okay. Sir, can we use rubber coating on hulls of ships?
Rubber coating.
Foul coating?
Rubber.
Oh dear. I'm sorry. I'm sorry I'm not hearing. You have to write it on a poster and hold it up because I'm missing a word there.
Okay, so I will try once. Can we use rubber coating on ship rather than epoxy coating?
Oh God. Can you use a something coating on ship?
Rubber.
Just type it.
You're going to type a message?
Yeah. They put
Good
it there.
idea. Okay, that's better, I think. I'm sorry. I I don't want to pretend I'm hearing if I'm not, because I'm not getting it.
Just hold.
Oh, a rubber coating. Can you use a rubber coating on the hull of a ship? I know it's done. I don't know much about it. I'm definitely not an expert. So I haven't encountered it, but I know that it's done. And I am absolutely useless as far as giving you information about it. Did you get my answer? Oh, okay.
Ah, yes.
So r- rubber coatings are used. They're particularly used, for example, for for an area where tugboats come up along the side, or instead of fenders, and they're used for that. This coating that I'm telling you about will actually withstand abrasion as well as the rubber will. So you've got a choice there. Does that answer that or not?
Yes, sir, I got it.
Okay, cool.
Thank
Good
you, sir.
question. I'm not an expert. I'm sorry. Somebody else.
No more questions, David. Shall we,
Well, no, I've cut you short by about 11 minutes.
shall we go with the movie? Like video.
Say that again.
We can,
Play the video. Oh yeah. Okay, cool. Now, at the end of this, I'm going to send this presentation to you again, the one that I've just gave. You're very, very welcome to distribute it to everybody attending. And at the end of it are my contact details. If anyone wants to follow up with a more detailed question or whatever, they can just write to me. I will answer any emails rapidly.
Sure, sir.
we can move.
Galen.
Are you showing the video or shall we play out?
Oh, am I showing it or are you showing it?
Present பண்ணிடட்டுமா?
We can show it.
I can show it. Ooh, I'll have to find it and drag it up. Hang on. It's quite long. I don't have it so handy. I'll have to dig it up.
Okay, we'll.
Oh, we will play.
You'll play it? Okay, good. I'll leave you to it, shall I?
Sir, speaker. தெரியல அப்ப என்னன்னு. ஆனா விட்டது இப்ப இதுதானே? இதுதானே சார்? அதான் இருக்கு. தெரியல. இல்ல சார், வேற sound வருது.
இல்ல கனெக்ட் பண்ணும்போது அந்த இது வரும்ண்ணா.
இல்ல, அது check பண்ணிட்டேன்.
ஏன்னா இதை கனெக்ட் பண்ணும்போது அந்த டச் பண்றதுக்கே சவுண்ட் வரும்ண்ணா. அது வரல. இப்போ அந்த இஷ்யூ ஆஃப் பண்ணு. இப்போ ஆன் பண்ண சொல்லுங்க.
ஆன் பண்ண